Hello and welcome to Project 2101 of this year's Summer of HPC. My partner Aneta and I worked on the analysis of data management and scheduling policies in HPC architectures. Most computer architecture designs today focus on reducing the latency of moving data between memory and the processor, otherwise known as the bottleneck. The bottleneck is a common feature in most von Neumann computer architectures. MIP, which stands for Mare Nostrum Experimental Exascale Platform, is a flexible FPGA system that seeks to explore various hardware and software core designs for exascale supercomputers. MIP proposes an architecture called the ACME, or the Accelerated Compute Memory Engine, whose unique features include a self-hosted accelerator. This means that the accelerator can perform and run applications within its environment, thus eliminating the need to move data to and from the host CPU. To achieve this, a vector processing unit and systolic array units are incorporated within the cores of the accelerator tile. These components can be optimized for vectorized and parallelized computation. In addition, ACME employs a decoupled architecture in which the memory operations are separated from the computation, thus offering a clean-cut approach to how sparse and dense workloads are handled. In the HPC domain, the number of checkpoints and executions that need to be simulated is high. Coyote is a new open-source, execution-driven simulation tool that focuses on the modeling of the data movement throughout the memory hierarchy, which gives an adequate output that we can use to compare the performance of the different memory reordering designs. Coyote is founded on two existing simulators, Spike and Sparta, which have been orchestrated to work in sync. While Spike handles the various instructions sent to the memory tile, Sparta handles the events that result from the execution of these instructions. MIP is a reference to the Roadrunner for its speed and efficiency. In the cartoon, Wile E. Coyote aspires to match the Roadrunners using his wits. This is precisely the goal of our simulator, to identify the best data movement and reordering policies that ensure a better leverage access pattern for applications, hence faster and more efficient computing. So come on, let's get into the simulation. Various memory operations are simulated in Coyote. The accelerator and the memory tiles communicate through the network-on-chip router. The commands, requests, and data are encapsulated into NOC messages, which go through the bidirectional router. An advantage of our memory tile is that its structure allows the reusability of some functionalities. For example, a scalar load operation is handled like a unit stride vector load with a loop iteration of 1. The types of vector load and store simulations include unit stride, non-unit stride, and indexed. For our example, we'll look at a unit stride vector load instruction. It begins with the accelerator tile sending out a vector load instruction to the memory tile through the NOC. This instruction has a number of parameters, namely the element width, the destination register, the start address in the memory the vector should be loaded from, and the thread ID. After traversing the NOC, the transaction is stored in the incoming queue. The queue then signals to the MCPU that an instruction has arrived. The MCPU in turn peeks into the queue to check whether the instruction is in fact meant for the MCPU. This is important because some instructions, such as those that carry data to be stored, are consumed by the microengine instead of the MCPU. Since the transaction is destined for the MCPU pops the transaction, essentially removing it from the queue. At this juncture, the MCPU needs resources for the instruction. It therefore checks whether the microengine and the vector address generator are available. The microengine is responsible for generating transactions for the instruction to be returned to the scalar core, whereas the vector address generator generates the memory requests. Once confirmed that the microengine and the vector register are available, the MCPU sends the instruction to both of them. In the vector address generator, the virtual address in the instruction is translated to the physical address using a translation lookup buffer. A memory request containing the address of the data to be fetched is scheduled in the bus queue. This step will be repeated multiple times until all the data requested is fetched. This memory request will then be sent to the last level cache. If the requested data is not found in the cache, the memory request is forwarded to memory. The data is then loaded from memory and put in the last level cache. It is then scheduled through the bus queue to be consumed by the microengine, where there is a slice of SRAM memory for temporary storage. Once all memory requests from the load instruction have been processed, the data in the microengine SRAM is packaged into a NOC transaction, which is scheduled for the outgoing queue and sent to the accelerator tile to be stored in the scratchpad.
Let's continue with the memory scheduler, starting with the high bandwidth memory description. The high bandwidth memory is a stacked double data rate memory that is connected via an interposer to the FPGA. At the bottom of the HBM is a base logic die. On the top of the logic die are stacked DRAM dies which are connected through silicon vias. Each slice of core DRAM die has 2 channels with 8 independent bank groups. The utilization of memory banks enables concurrent DRAM main memory accesses and increases memory bandwidth. All banks within a channel share the command, address, and databases of the channel. Each bank has a structure of a 2-dimensional array of rows and columns. When the processor generates a memory request, the data is searched after in all levels of cache memory, and if the data is not found in the last level cache, then the memory controller looks for the data in the main memory by sending the physical address of the data via the memory address bus. On the data access, the entire row containing the data is copied into a structure called the row buffer. A subsequent access to the same row can be served from the row buffer itself, and it does not need to access the array. This is called a row hit. However, when accessing a different row, the previous row of data must be returned, and then the next row can be accessed. This type of access is called a row miss or conflict. In a system where multiple cores share a common memory interface, concurrent memory requests from different threads executing on different cores can interfere with each other while accessing the shared DRAM main memory system. This is also called inter-thread or inter-application interference, and it degrades system performance and slows down applications. To mitigate inter-application interference, a state-of-the-art memory scheduler called the Blacklisting memory scheduler, or BLISS, can be implemented. BLISS separates applications into the following 2 groups: interference causing and vulnerable to interference. When a large number of consecutive requests are served from the same application, other applications will likely stall. Therefore, BLISS counts the number of consecutive requests served from the same application. When this count exceeds a threshold, BLISS places the application into the interference causing group, also called the blacklisted group, and other applications are placed in the vulnerable to interference group, that is prioritized. BLISS has 2 components, the blacklisting mechanism and the memory scheduling mechanism. The blacklisting mechanism needs to keep track of the following 3 quantities: the application ID of the last scheduled request, the number of requests served from an application, and the blacklist status of each application. Before a request is issued by the memory controller, it compares the application ID of the current request and the application ID of the last scheduled request. If they are the same, then the number of requests served counter is incremented. However, if they are different, the counter is reset to 0, and the application ID register of the last scheduled request is updated with the application ID of the current request. If the number of requests served counter exceeds a blacklisting threshold, then the application ID of the current request is blacklisted and the counter is reset to 0. The blacklisting information is cleared periodically. The second component of BLISS is the memory scheduling mechanism, which uses the blacklisting information to determine the scheduling priority of a request. The othermost priority belongs to non-blacklisted applications requests because they mitigate interference. Then row buffer hit requests follow because they optimize bandwidth utilization, and finally all the requests are prioritized for forward progress. BLISS does not implement total order-based ranking of memory requests, which leads to lower complexity, so that strict double data rate memory timing protocols can be met. BLISS also helps to achieve higher system performance and fairness, while incurring low hardware cost and scheduling latency. This brings us to the end of the presentation, where we want to express special gratitude to our mentors and to the whole MIP team at the BSc.